full extent of the question though. So there are definitely data sets though.
I think I guess it just seems more intuitive to me that to be learning from what they do.
Oh, I agree, yeah. Maybe we should head out. But no, it's true, but you're
Are Jim and Aiden coming? Neither of them? Okay. Okay, I'll grab one more chair for him.
Yes. So, could you check back there and see, like, I'm not seeing my slides. Ask the guys back there if they should. In the booth, in the booth back there. I'll try plugging it in again, but. Oh, it's good. Thank you. Okay, any logistical questions before we start? All right. Yes.
Is it possible to upload the slides for today's lecture?
Should be there.
It redirects the YouTube videos for last class.
Maybe I broke the link. Do you guys know how to find the link for the slides?
We'll try.
They're in the Google. They're in the shared Google Drive under Lectures for Web. So I must have just copied the wrong link when I was putting them in. Sorry about that. All right, thanks. Sorry about that. Yep. Any other questions? So let's see, auditors, there are a couple people that talked to me about auditing after lecture. You are welcome to come to the lectures or watch them online. If you need to get access to the lectures through B courses, we would ask that you not do the homework assignments because they're in teams and things like that, and even I think it'll confuse things on the quiz. So just send mail to the CS267 link that I had in the last email, and we'll make sure you get set up on B courses so you can watch that. And otherwise, I think we're trying to clear the waiting list. I think we've got most people in, and the Homework 1 teams have been assigned, and it should be available to you inside of B courses. Okay, so any other questions? Yes?
Did you say for auditing we can take the courses after each lecture? Or
I think they cannot. Is that right? Okay, because I think it's going to confuse the grading and stuff like that. So we would rather you not take the quizzes. Sorry, but yes. I think that was a different answer. Okay, great. So today I'm going to talk about single processor memory hierarchies. It will be a review for some of you who are have a computer science undergrad degree, for example, and or have taken computer architecture courses before. But I'm going to also tell you it's going to be pretty compressed. So it'll be maybe a review for some of you and new material for others. We're going to talk about a specific example, which is matrix multiplication. That is the first homework assignment. So so stay awake and alert, and we'll try to give you some hints as to how to do the first homework assignment. So motivation here, remember, this is a course on parallel computing. Parallel computing is primarily about performance, so this is also really a course on performance programming. So that's one of the things that this particular lecture is really about how to get performance out of single processors, and that's because if you're going to try to get performance out of parallel processors, the first thing you need to do is worry about how slow your serial code is. Most parallel applications run at under 10% of the peak performance of the machine. So think those top 500 numbers that we talked about last time. That would be the peak performance of them, or the LINPACK number would be pretty close to the peak performance. But for most real applications, before you even start parallelizing your code, you lose a lot of the performance just in a single processor. And that happens because it's mostly about moving data around. Most expensive thing you do, if you learn nothing else from this course, the most expensive thing you do on any computer is move data around. And so in order to understand what some of those costs are, we need to really look underneath the hood. And I'm just wondering what that clicking noise is and whether
Slack.
that's Slack coming through my computer. Thank you. I will turn that off. We are communicating by Slack, but that's why we have the whole staff here, so they can tell me what to turn off. Okay, great, thank you very much. All right, we will go through this one. Okay, so how might you react to today's lecture? This computer architecture stuff is fascinating. I want to go and design parallel architectures or even serial architectures. The optimization algorithms that you use are fascinating. I want to go learn more about these algorithms and how to optimize these to take advantage of these memory hierarchies. I hope I don't have to learn much more about this, because I hope I can just call libraries that other people have optimized for the parallel hardware so that you don't need to worry about it. I wish the compiler would just do everything for me and I wouldn't have to think about any of this stuff. I would like to write a compiler that would do everything, and so nobody else would have to worry about any of these details. Or I want to understand something about the meltdown and Spectre bugs, which are related to memory hierarchy optimization. So these are all different ways that you might think about today's lecture, and I'm sure many of you will have different approaches to this. What are we going to do specifically? I'm going to talk about the cost of things on modern processors. Then we'll go into more detail on memory hierarchies, and we'll talk about parallelism on a single processor, because even within a single processor there is some parallelism. And then we'll do a case study on matrix multiplication. Okay, I'm going to start with a very idealized processor and talk about what things cost. So in an idealized processor, we have the processor itself and we have memory. Okay, so think of that as DRAM, the separately purchased memory that you get when you're buying your laptop or whatever, and then you've got your processor here. So whoops. So let's see, what do we do when we write some program? We write a program and name some variables. Those variables are things like integers, floating point operations, double precision floating point, pointers. Those kinds of things might be are kind of basic operations. They might take up a single word of memory. And then there can be other more complicated variables in your program, such as arrays and structures and things like that. That would be a larger chunk of memory. The processor is going to perform operations on those variables, so you can do arithmetic and logical operations, and it's also going to branch. It's going to perform logical operations to figure out which part of the code to run, do loops and function calls and things like that. And so, oops, sorry, I put a little bit more detail in my processor. I have the arithmetic unit there in order to do the arithmetic operation. I've got the control part of the processor inside there in order to do to execute the control operations. Now, in a really idealized world, each operation has the same cost. Okay, so we've got add, we've got multiply. Those are the only operations we've really talked about, and we just worry about the cost of those arithmetic or say other kinds of those arithmetic operations. But a slightly less idealized processor of this uniprocessor, which is a single processor model, says that these are really words in memory, these variables, and they have different sizes, and that will be important to you when you're trying to figure out the performance of them. They're going to take up a certain number of bytes, so a character might be a single byte, and a double precision would be a 64-bit operation. So those things will matter when you start worrying about the details of the performance of the processor. When you perform the arithmetic operations, it will only perform those operations on values that are in registers. So you got to get the variables out of the memory and put them into a register before you can compute on them. And And then the cost, in the cost model, we might assume that the control operations and the load and store operations that are moving data from the memory into the processor are free, which they are not. But in an idealized model, and this is, by the way, the model you typically learn about when you're doing algorithmic analysis. So if you've taken CS, you think a little bit in CS70, but certainly in CS170, or in any other department where you've taken algorithms courses, you tend to count the arithmetic operations. So you might say something like, matrix multiplication is an order n cubed algorithm. It does order n cubed floating point operations. It does, more precisely, 2 n cubed floating point operations, where n are the dimensions of the matrices. Okay, so we tend to talk about that a lot, but that kind of hides the fact that there's other very expensive things happening besides the multiplies and adds that are inside of matrix multiplication. So the other thing you need to understand is that your code is getting translated from your higher level language, whether that is even a pretty low level language like C or C++ into, or Python or Java or MATLAB or whatever, all the way down into some kind of code that actually runs on the hardware. And at this level, we're going to worry about the fact that we need to get the variables out of the memory and into the register so that we can compute on them, because in the assembly language level, this lower level code that's executing on the processor, as I said, you can only do, say, addition operations on things that are in registers. So we've got just a tiny bit of code here, a single statement, C is equal to A plus B. What does it actually turn into? The compiler does this for us, so you don't normally have to worry about it, but you will need to think about it a little bit when it comes to thinking about the performance of your code. So you have to load A into one register, load B into another register. Then you do the addition operation, and this is taking R1 and R2, those two register values, and putting the sum of them into a third register, R3, and then you have to take that register R3 and store it out into memory. So you've got 3 memory operations that are going between the memory and the processor, and then you're moving the data back and forth. And so that's important to understand. So the compiler is really doing a few different things for you. So one of them is it's putting these load and store instructions into the code for you. It's translating that higher level language into the lower level language that runs on the hardware. It also checks that the program is legal in that language. It makes sure, for example, that it is type safe, or it makes, it looks at other syntactic errors to make sure it's actually a program that it can run. But then it does this translation into assembly code, and it will also optimize the code for you. So it will try to make that code run faster on the hardware. So just a little bit about compilers and registers, and what's called memory management or register management, register allocation. A compiler does register allocation to try to figure out how to best use a fixed set of registers. So they're not a large number of registers in the processor. You've got all of these variables sitting out there in memory. It has to figure out which one should it put into a register. Well, it can do it just sort of one operation at a time. Every time it sees an add, it can go get one variable from memory, another variable from memory, do the add, and then put the results back in memory. But given I've said that the most expensive thing you do is move the data back and forth, you'd like to leave them in registers if you're going to reuse some of those values again. So here's a little bit of code with a few statements in it, and here's some of the optimized code that the compiler might spit out for that, where you load C, and then you load D into a different register, and then you load B into another register, and then you can actually do all of the computations there, the 2 additions and the subtraction, just using the values that are in those 3 registers. And the process of figuring out which values can I reuse in the register is called register allocation. And it's something that compilers are very good at. It has taken many years. There's a lot of theory on how to do this. One of the techniques they use is called graph coloring. In fact, the very first Fortran compiler that was in the 1950s actually did some of this register allocation inside of it. It wasn't just doing kind of one load and store for every single arithmetic operation. But people got better at it, and they realized that it was equivalent to a problem called graph coloring, and that little graph there is showing edges between the variables that have to be in memory at the same time, given some assumptions about which variables are called live, that is, which variables are going to be used later in the program. So I won't go into detail on this. If you want to take 164, I think you would learn a lot more about register allocation, or one of the graduate courses, 264 if we teach that one again, that you'll learn about this kind of algorithm such as register allocation. And the just-in-time compilers, for example, for languages like Java, will do things like this, maybe even a different technique. But it's a very expensive algorithm, but it is used in practice on a relatively small number of registers. Okay, so the compiler does some other things to optimize your code. It manages those load and store instructions. It's trying to minimize the total number of loads and stores because they're expensive, and so that we don't see them in the code because they're generating them, but it'll also try to reduce the total number of them. So what are some other things the compiler will try to do? And this is really just a quick list of things, and you're going to get a lot more hands-on experience with this in homework 1. And when we get to the case study, I'll talk a little bit more about some of these optimization as well. One of the things it can do is it can unroll a loop. So if you've got a loop that says for I equals 1 to 4, it can just turn that into 4 different copies of that code and get rid of the loop that goes around it. Okay, and that can be useful because that control structure, the loop itself, requires some overhead. It slows the processor down, and we may get some sense of that when we talk a little bit more in detail about what the processors are doing. It can sometimes take 2 different loops, one's up here and one's down there, and merge them together. It can interchange the loops in the order in which they're running if they're nested loops. It can get rid of code that is never executing. That's called dead code elimination. That tends to not really speed up the performance so much, except it can make the code smaller, which can make it the code itself then take up less memory, which can be useful in terms of performance as well. It can reorder the instructions to improve the register reuse. It can try to move things around in the code. So for example, the value in R1 gets used multiple times. And it can turn expensive operations into cheaper operations. So for example, if you've got an integer and you're multiplying it by 2, it might be able to turn that into a shift operation. That's just shifting it over by 1 bit. And so why do you need to worry about this in this course? Well, you're not going to worry about all the details of exactly what the compiler is doing, but what you will find in homework 1, and I'll just give you an example of this from previous homework experiences from students in this class, is they are looking at matrix multiply, which has some loops in it, and they try to unroll one of those, say the innermost loop of that matrix multiply code, and when they do that, the compiler decides to unroll it some more for them. And the compiler didn't unroll it at all in the first place, but when you unrolled it a little bit, it somehow got smarter and unrolled it for you. And so sometimes the compiler can do things that don't actually seem like they're optimizing the code. They're actually making it slower, and so then you have to sometimes interact with the compiler to try to convince it to either do an optimization or not do an optimization. Questions? Okay. We're going to talk about memory hierarchies. This will be a quick tutorial on what memory hierarchies look like. And we'll talk about temporal and spatial localities, as well as the basics of caches and a little bit on some benchmarks. Okay, so we've got our idealized model. We're going to make it slightly less idealized. We're going to point out the fact that these memory operations are more expensive. So and for each one of those memory operations, there can be what's called a latency cost and a bandwidth cost. And we'll say a little bit more about that in a minute. So since I'm going to talk about the bandwidth of the memory system and the latency, let me tell you a little bit more about what they are. So you've got a pipe that's connecting the memory to the processor. And you can think about how long does it take to get something from the memory into the processor. So that would be the latency of the operation. And then the bandwidth is what is the rate at which you can get data between the memory and the processor in either direction. So you can think of this as a pipe with water going through it. In this case, we have bits going through it. And the same thing is true if we're looking at a network. In this case, we're looking at really the connection, the memory network between the processor and the memory system. So we've got a low bandwidth pipe, which is really skinny, so that it's kind of independent of how long it takes to get something through there. There's just a rate at which you can get data through that versus a high bandwidth pipe. And that's in contrast to high latency versus low latency, where we've got a garden hose. You've got a short one, and when you turn on the faucet, the water will come out very quickly. If you've got an empty water hose and you turn on the faucet, it'll take quite a while if the hose is really long, and that's the latency. And so both of these things can be important in the performance, and it depends a little bit on whether you've got lots of work that you're doing in order to fill up that garden hose with a lot of work, or you're really waiting for just 1 drop of water to start at the faucet and get all the way out the end. So historically, the memory systems have not kept up with processor performance as we've been reaping the benefits of Moore's law and having faster processors coming from that higher transistor density that I talked about last time. So even though processors were getting faster, this is what is called the memory bandwidth gap, or the difference between the number of floating point operations per second and the number of words per second that you get. Okay, so if you are just worried about sort of the raw speed at which you can do things on the system, then you have to worry about how fast can you get data out of memory versus how fast can you consume data by doing, say, floating point operations on this. And this is a graph from John McAlpin, who's at the TAC Center at Texas. And what you're seeing is over the history, this gap between the ratio, that is between flops and words, or he's looking at gigaflops over gigawords, has been growing over time. And notice that it's a log scale. So it started in the early 90s, where it just took a few floating point operations. The cost of moving a word kind of in the steady state in the bandwidth case was only about a few arithmetic operations, floating point operations, whereas today it might be more like 100 arithmetic operations every time you do a load and store. So that really affects what we run on the hardware. It means that you really need things that are going to have a lot of arithmetic work if they're going to run it anywhere close to the peak arithmetic performance of the machine. Now, a lot of people will say, and I've heard this over many years from the scientific application users community, my code is bandwidth limited. And they say my code is bandwidth limited because it's not running at the peak performance of the hardware, of the stated floating point rate of, say, the Cori system or whatever. A lot of times it's not actually bandwidth that's limiting it. It is actually latency that's limiting it. And so that's the difference between, the length of the garden hose and the rate at which you can get water through the garden hose, or in this case, get words through the memory system. And so this red line is showing the gap between the memory latency and the gigaflops per second. And so that's even a much bigger gap, where it may take you tens of thousands, or at least thousands of arithmetic instructions are equal to the cost of one memory operation. Okay, so really very, very different costs. So what are we going to do about this? Well, what the hardware designers do about this is they put in a memory hierarchy. And they say, well, if it's going to take you a really long time to get to memory, or even worse, to get to disk, or to get to some kind of a tape or a cloud storage or whatever, I better put something in between that processor that's much faster memory and that really slow memory system that I'm trying to get to. And so what we'll do is we'll put in a memory hierarchy. And that hierarchy is trying to improve your average case behavior. It's not speeding up the speed of the slow memory system, because that is what it is. But it's going to put some fast memory in between, so that most of the time you're going to be accessing data that's in the fast memory. And only rarely will you hopefully have to go to the slow memory. So that gives you the perception that the memory system is faster because there's some fast memory sitting in between there and the really slow memory. So it's used to improve the average case. And it's depending on two things: spatial locality and temporal locality. So what does it do? What is spatial locality? Spatial locality says that if I've accessed one variable sitting at one location in memory, I'm very likely to access the one that's right next to it. And that will happen, for example, because you have an array of variables and you're running through that array. And so if I've laid them out in memory, if I access the first one, I'm going to access the second one, and so on in order. And so what the memory system will do automatically, kind of behind the covers for you, is if you load this first element of that array, it will load maybe another 7 elements along with it. It'll take a chunk of 8 words and put them into the fast memory for you. So you only see the cost of that one, that slow memory access on the first one. The second thing it will do is take advantage of temporal locality. It will save that thing in the fast memory for a while, as long as it sort of fits in the memory and doesn't get knocked out by something else. It'll save it in the fast memory, and so that the second time you use that same value, it will still be in the fast memory. And that's taking advantage of temporal locality. That is reusing an item that you have previously accessed. Okay, questions? Straightforward. Okay, so now a little bit about how caches work. We're not gonna try to go into details here, but think about your memory system as this big chunk of memory where you can store values inside of it. So it can store things like the number 42 or the number 13, or maybe a little bit of genomic sequencing data, ACTG, or a little string, weight, and scene, and things like that. Okay, so those are the values that are sitting in memory. Each one of them is sitting at a different address. And so the number written next to it in binary is showing the address at which so those are all contiguous in memory at those locations in memory. And then I've got my processor over here on the left. And then what I've done is I've put my fast memory, my cache in between there, and it will save just a little bit of data. So in this little cartoon, the cache only can hold 4 words of data. Okay, and so in this case, the first word it can hold is going to be anything that lives at the address that ends with 00. The second word it holds will be anything that ends with 01, and so on, 10 and 11. And so you can see that at 00 in actual memory is the genomic string ACTG. That's sitting there in the cache right now, so if you need to use it again, it'll be there. It also has the word weight that came from 01 and so on, but it's a kind of an arbitrary set of things that are in slow memory that happen to be at those that location in the cache. And the hardware handles all this for you, so you don't really need to worry about it too much, except for the fact that you need to worry about the cache is not actually very big. It's going to be a lot bigger than 4 words, but it's not very big. And so a cache hit is going to be anytime the processor does a load and store instruction, and that value or that location that it's trying to get to is actually sitting in the cache. So the value is sitting in the cache already, or if you're storing to it, it's been kind of allocated there so you can write to it. And then the hardware will make sure that those values that you write into the cache will move back to the slower memory. So that's a cache hit when you get to use the data that's in cache, and it's a cache miss in the other case when you have to go out to the slow memory. And so this one's going to be the expensive case. Okay, questions? All right, so a little bit more of cache basics. The other thing you need to know is, as I said, the memory hierarchy is going to take advantage of spatial locality. It's going to guess that the way a lot of programs are written, if you access one word, you have a much higher probability of accessing the word next to it than some arbitrary word in memory. So a cache line is going to be the unit of memory that it's going to load up every time it does a cache load when you do a cache miss. And so it takes that value from the memory, but it's actually going to get a contiguous chunk of things. So because I'd written this kind of silly example where I had these various values sitting there contiguously in memory, it's going to load that chunk of things into a single cache line. And so that's called a direct mapped cache in the basic case where there's just one address for any given sort of bit pattern for a given range in the cache. So this particular line in the cache, I don't know if you can see the characters up there, that it's taking everything that lives in memory at location, any address that ends with 1100. Okay, it's a little bit bigger than the other cache, but so it's not. We've now got 4 bits that are determining our cache line size. Sorry, the number of lines that are in the cache, and so we're gonna load this chunk of values in. And the hardware will keep track of the fact that if you want to access that later, it will one of those other values, it will be able to find weight or scene or whatever it is that is in there. But it's direct mapped if everything that lives at the location that ends with 1100 in your actual memory goes into the same slot in the cache, and that means you only get to have one of those values in your program. So you can imagine that you can write a program pretty easily that's going to jump through memory, for example, and keep knocking that one cache line out of the cache that you need. And so in order to get around that problem, caches are often built with some level of associativity that says, well, I can't keep arbitrary sets of data in cache because that's very expensive to find anything in the cache. But what I can do is say, well, I won't just keep one cache line that lives at 1100. I'll keep 2, which would be a 2-way associative, or 4 or something like that, or 8 of those values that all live at have the same trailing bits in the memory location. So I've got a little bit of associativity. And so what this says is that I don't have complete control about what you want to put in the cache. If you wanted to say I'd like that value and that value and that value to all sit in the cache, they may or may not fit depending on whether what addresses they happen to live at in the actual memory, and also what kind of associativity you have. Okay. Yes?
The example, is that Is that an example of like four-way associative?
So the example at the top is supposed to be showing a cache line that stores 4 words in it. And so that's just a one-way associative cache right now. If I wanted to make it a two-way associative, at least the way I would have drawn this is had another little purple box or blue box, whatever that is, next to it that says here's another set of 4 words that are also living, that also end with the address bits 1100. And then if it was 4-way associative, I would have 4 of those little blue boxes, these little blue boxes right here. Okay, and the cache has to keep track of where they came from in memory, so it actually has to remember, oh, okay, they all ended with 1100, but it needs to know exactly which one it was, because when you give it an address, you want to say load on an address, you're not going to just give it the last 4 bits of the address. You're going to say, give me something that is at this address, and it'll look it up in the cache and say, so if it's just a one-way associative, that is a direct map cache, it's very easy. It can just kind of look at, well, it looks at those last 4 bits, but it has to still check to see whether that's the value that's in the cache. And if it's associative, then it says, well, is it any one of the values that's in the cache? Any other questions? Okay, so real systems have multiple levels of caches. They will have typically an on-chip cache, often an L1 cache. They put that something on chip because it's very expensive getting data in and out of the pins. So the pins on the processor chip are often one of the sources of both latency and power and bandwidth limitations and things like that. So if you can put the cache on the chip, then once it's there, it's very fast to access it. But you can't fit very much on the chip. So there's this trade-off in building your caches, which is if you make them too big, then you can't fit them on the processor chip. But even when you go off chip and you have an off chip cache, which you'll have, then a larger cache has more delays. And maybe it's somewhat clear from talking about associativity. If I have this list of things, I have to kind of go through it and figure out is the one I'm looking for in there. Even if it's a direct mapped cache, you have more computation in order to figure out. You have to look at more bits and things like that, and you have to check these addresses in order to figure out whether something is in the cache. So. It takes longer when you have a larger cache, and so the type of memory that you use for a cache, even an on-chip cache, may be different than the kind of memory that you're using for your main memory. So the main memory you might be buying for capacity, and the cache you're buying for performance, and so those are going to give you different trade-offs. So just as an example, there's an old system that many of us loved, a supercomputer called the Cray T3E that had a little bit of specialized hardware around it. It had a alpha processor in it, and it actually took one of the levels of cache out of that system that was in the standard workstation at the time configuration of that processor. And the reason is because it was trying to speed up the time to get to the actual slow memory. Okay, so that may seem a little bit counterintuitive, but the idea was, well, if what happens if you do a cache miss, if you have to check every level of cache to get all the way out to the slow memory, then it actually slows down the time to get to the slow memory. And so if your application workload is such that you're either really localized within this data that's sitting in the cache, or you're all the way, you're probably looking at some sort of random looking memory location, then you might as well not have that second level of cache if you're not going to hit in it with fairly high probability. The system that you're using on Cori, at least for homework 1, is the Intel Haswell processor. It has 4 levels of cache. The 4th one is what's called a victim cache, which is just some data that is being kind of on its way out of the cache system, but it's preserved there at the last level. So things don't get loaded into it from memory, directly from memory, but they get pushed out from the level 3 cache. So there's a bunch of different ways that these systems can be designed, and there's also, by the way, other levels of the memory hierarchy that you may need to that you may run into in performance. Probably the most important is the virtual memory system, which is based on the pages that the operating system manages. So now you've got the operating system, which is moving data around for you automatically and figuring out what data this application has access to. So it's giving you some protection over that, but it's also then is mapping those addresses. And so there's a little table called the translation lookup buffer, which is the TLB, which is going to keep track of the addresses that are mapped in memory. And it turns out that although I've talked about it as a pure hierarchy, there are times when it isn't actually a hierarchy, where the things that you can map in the TLB are actually smaller than the things that you can map in the lowest level caches. So it can get very complicated, and as a result, the performance can be a bit confusing. So what do you do about this when you're trying to make an application run fast on one of these what I'll call memory hierarchies for now? What you're going to do is try to write your program in such a way that you have very good temporal locality. So you're going to try to write it in such a way that you're going to reuse the values that are in the cache. And this is sometimes called bandwidth filtering. That's another thing the cache is doing, which is preventing you from having to go out to that slow memory, so preventing you from consuming the memory bandwidth by just using things that are in the cache. So you're going to want to reuse things as much as possible, and you're going to want to put things next to each other as much as possible. And you may want to worry, for example, about exactly where things are in a cache line so that you're using a complete cache line and things like that. You also may want to use vector operations, which I'll talk about in a minute, that allows you to load a chunk of memory in a single instruction, and that's going to require what are called SIMD instructions, or vector instructions are going to require that you have a set of addresses that are next to each other in memory, and you load explicitly in the compiler will generate an instruction to load a set of values that are next to each other in memory. And you may want to take advantage of getting better bandwidth, and I'll talk about this a little bit more in a minute in terms of how to think about what the processor is doing to get better bandwidth by allowing the processor to issue multiple read and write statements in parallel with other read and write operations. So this is overlapping the cost of the read and write operations, and there's both techniques called prefetching, where you issue a read that says, I don't need this value quite yet, but I think I'm going to need it in, say, 2 iterations of this loop. So issue a load right now, because then by the time that memory comes back, by the time I'm ready to use that value, it's going to be sitting in the cache. And you can sort of do the opposite with writes. This is similar to the victim cache I talked about before, but you can have a write buffer that says, I don't want to wait all the way for my write operation to make it all the way out to my slow memory. I'll put it in a little buffer, and the hardware will move that stuff out to the slow memory when it can. These are actually generating a little bit of concurrency inside of your serial processor now, and so we start worrying about parallelism, because we have to worry about the fact that if you are prefetching, you're kind of doing a memory operation in parallel with the computation that you're doing in this earlier iteration of a loop. Okay. So how much concurrency do you need in order to get the bandwidth of this system? And there's a law called Little's law from queuing theory that says that the amount of concurrency you need is equal to the latency times the bandwidth. So for example, if we have a latency of 10 seconds, so this is not a memory system, but think about some system, because it's easier to do the arithmetic. So I've got a system where it takes me 10 seconds to read something from memory, really slow. Maybe it's going off into the cloud and who knows where. And then my bandwidth says I only can get 2 bytes per second. So what that means is that I need 20 bytes in flight so that I'm going to see basically the bandwidth utilization. That is, I'm going to see something coming back at 2 bytes per second, rather than seeing each one of them is costing me 10 seconds. So questions about that? This might be, I'm going to do a processor example in a little bit, and that might make it a little bit easier too. So another graph, which or some data from John McAlpin, says that on one of these modern processors, this was fairly modern, an Opteron processor, so 2005 era, I guess, not so modern. The latency was 60 nanoseconds, and the bandwidth was 6.4 gigabytes per second. And what that means is that you needed to have 384 bytes of kind of parallelism in flight. So you're trying to issue these load instructions, for example, to keep the memory pipes busy loading that data, and so that means that you needed 6 cache lines given the length of those cache lines. So and so in order to keep the pipeline full, you had to keep these 6 cache lines in flight. Okay. So I promised to tell you a little bit about how you measure these things, and John McAlpin also built this stream benchmark that's widely used. There's a number of different benchmarks for doing things like this, but these are probably the most popular at this point, is a set of benchmarks called the stream benchmark, or stream benchmark suite, which is for measuring the memory bandwidth of a system. And it has 4 different little kernels inside of it, just little tiny programs. The first one is just a copy that copies an array A into an array B, all the elements, one at a time. And then there's one called scale, which is almost the same thing except is multiplying everything times the first array into the second, something that's adding 2 arrays together, and then an operation called triad, which is taking, what you can see there is multiplying some scalar value, so just think that's just a constant, times a element of an array C, adding it to an element of array B, and then putting the result in array A. That comes up because that particular pattern is very commonly used in a lot of computations, and we'll see that come up in, or something similar to that, at least in matrix multiply. So n is the value in these loops is chosen. N is chosen to be very large, so that the array is larger than the cache, and that way you're going to see what's the rate at which you can get data in and out of the cache. And you repeat it a bunch of times, and then you look at the different measurements of it. So you may find that you want to see if somebody else has measured the stream benchmark for the processor. I often find it's very helpful to measure it myself, because you get a lot of intuition about what's going on, and sometimes you don't see the bandwidth you're expecting to see. The manufacturer or NERSC may tell you, here's the memory bandwidth that you should be able to see on this, but running these benchmarks will tell you what you actually are likely to see, or maybe there's something you need to do in the compiler to generate the right code to get to see that kind of bandwidth. Okay, we're going to talk next about parallelism that's inside of the single processors, so instruction level parallelism, and then something called SIMD parallelism. I've already referred a little bit to that in thinking about these memory operations, and then we'll finally talk about some special instructions that are in the processor. So I've sort of referred to this fact that you want to have multiple memory operations in flight, but processors themselves use this idea called pipelining in order to give you better performance than what you would get by just waiting for each one of those operations to complete one after the other. So this is a example that Dave Patterson likes to use, which I think is very helpful because it's very intuitive to all of us, whether you've looked at computer architecture design or not, and is the problem of doing your laundry. Okay, so you're doing your laundry, and you've got a washing machine that takes you, maybe you're at the laundromat, you've got a washing machine that takes you 30 minutes, you've got a dryer that's going to take you 40 minutes, and then folding, let's say, takes you another 20 minutes. Okay, so the total time to do a single load of laundry is 90 minutes, right? It's just the sum of those 3 numbers. So that's the latency of doing laundry. And we're not actually going to do anything that changes the latency of laundry. It just is what it is. It's a cost of washing it, drying it, and folding it. Okay, but what we can do is say, well, if we actually have multiple loads of laundry, we don't have to wait for the first load to be folded before we start the second load. And so even in your own home, if you've got a bunch of loads of laundry that you need to do, you can start the first one, and you all do this, I'm sure. You start the second load of washing maybe as soon as the first load of washing is done. Now it turns out you're often waiting on the dryer, right? Because the dryer is the thing that takes the longest for all your towels and stuff like that. So that's going to be your bottleneck in terms of how long this takes. So this is called pipelining because I just have one washer and one dryer and one person, for example, folding laundry. And so I'm not doing any parallelism between them right now, but I am going to use the washer and the dryer and the person, the folder, all in parallel with each other. So that's called pipelining. So in this example, if you do a sequential execution without pipelining, each one of those laundry batches takes 90 minutes, and so the total time is 6 hours, so 4 times 90 minutes. In the pipelined execution, then I can do, I have to do the first load of washing, then I have to do the 4 drying loads, and then I have to do the 1 folding at the end. And so the total time that it takes is 3.5 hours. And so the bandwidth in this, which is the number of loads that you can get per hour, it has, you can do 4 loads in 6 hours without pipelining, but you can do 4 loads in 3.5 hours if you do the pipelining. And so you're getting a rate of 1.5 loads per hour with pipelining. as opposed to 1.67 loads per hour without pipelining. So the pipelining doesn't change the latency. That first load of laundry is going to take you 90 minutes no matter what, but the rate at which you get them through and the bandwidth of the system is going to be faster, and the speed up is given by the number of stages that you have and also by the slowest pipeline stage. So in this case, the rate at which you can get things through is limited by that 40 minutes for the system, for the dryer to work. Okay, questions? Okay, and so I might want to talk about what is the bandwidth of the system. And so that's that 1.5 loads per hour that we can do. That's the blue line at the top. And how much do I actually see in terms of how close do I get to getting 1.5 loads through per minute? If I only have one load of laundry, I'm going to get pretty low bandwidth utilization. I'm going to actually still run at that, just that 1 2/3 loads per hour. So I'm down here at well under a load per hour. And whereas if I have a bunch of loads that I can do, I can pipeline them and I'll start to get closer and closer to that 1 load per 40-minute number. And this is the same thing that we'll see when we look at memory bandwidth numbers and when we look at network bandwidth numbers and things like that as well. So how do processor designers use this? Well, they use this idea of pipelining because there's a bunch of different things that the processor has to do, and we will not go and talk in detail about all the different pieces of this, but for example, it fetches the instruction from the code, and then it has to decode it, has to figure out exactly what that instruction is doing. It's going to do some address calculation, that is to try to figure out what are the load and what are the variables that are being accessed inside of that, or the registers and things that are being accessed by that, and then it's going to do a memory access if necessary, and then it's going to write back. And so what it can do is run these things. It can take one instruction, and even though the first instruction hasn't finished, it'll start the second instruction going through, say, the instruction fetch stage, and through pipelining, then you get the bandwidth of the processor to run faster than the total cost of getting all the way through those different stages. And so it's also, by the way, this pipelining idea is also used inside of arithmetic units. So if you just ask how fast does it do how long does it take to do a floating point multiplication, it may be 10 cycles to do a floating point multiplication, because multiplication is fairly complicated, but you may be able to get a multiplication done in every cycle. So if you're doing a whole bunch of multiplies in a row, they may appear, kind of each one of them, to just take a single cycle. Okay, questions about pipelining? Okay, so the next thing that comes up is a little bit of parallelism that is really much more under software control. And this is called single instruction multiple data, or SIMD parallelism. We will talk more in a little bit later about this kind of parallelism that comes up at a larger scale across parallel machines. But in this case, all we're talking about is kind of making our registers bigger. Remember, that register could hold a single word that you're going to do a plus or minus or whatever on. But we're going to make the registers wider so they can hold, say, 4 values inside of each register, and then we can do the same thing on every variable, every value that's in that register. So for example, in traditional processor, each one of these registers just holds a variable, say x and y. You add them together, you get the result x plus y sitting in the register. But in a SIMD processor, the register can hold 4 variables, 4 values, and and then in a single instruction you can load those 4 values, and you can in a separate instruction add them together, and then you get the result in a register which has got all 4 sums inside of that register. And these instruction extensions, as they're called, these SIMD extensions on different processors, these are on standard x86 sort of processors. They're a little bit different on each machine. You'll be using Haswell in this course that has AVX2, which is a 256-bit wide register. And so that will give you the ability to do operations across all of the words that you put into that register. And then it can also do something called a fuse multiply add that I'll talk about in a minute. The second processor that you may be working with in this class is the Knights Landing processor. That's on the Cori system that I mentioned that you are getting access to. It has both a Haswell partition and a Knights Landing or KNL partition. And so what you will find later in the class, for this first homework, I think you'll be working with Haswell. But after that, you may have some more flexibility, certainly when you get to the final project, and you will find that you may want to use the Knights Landing part. So for example, on an Intel processor, how many things you can fit in those registers depends on what you're doing. You could fit, say, four floating point, so 32-bit values, 2 double precision values, or 16 bytes of values. And exactly what you can do on them depends on whether the whether the instruction set allows you to, say, do something on 16 bytes worth of characters as well as singles or doubles. All of them, I think, would handle both single and double precision floating point operations. And one of the challenges, though, of using these things is they have to be contiguous values in memory. So they're certainly going to be contiguous in register, right, because you're putting them into this one chunk of this one register. But the way the load and store instructions work, those SIMD load and store instructions, is they have to be coming from the same location in memory. Contiguous locations in memory. This is something that people are often trying to generalize in the architecture. It's much more expensive and much harder to implement something that says, I want to take this value from this location and something else from 16 words later and another thing from 32 words later and so on. That tends to be much more expensive to implement. As you can imagine, they might not all be sitting in the cache, so oftentimes you also have to load things that are going to be cache aligned. That is, they're kind of starting at the place that a cache line starts. And so you do need to worry a little bit about what addresses things are sitting at in memory. And there are sometimes instructions once you get the values into these longer SIMD registers that you can use to move them around. We'll see something similar, and we will have a lecture by John Owens, who is one of the experts on optimizing code for GPUs. He's at UC Davis and will come in to give our guest lecture, fortunately, on this, because he really is one of the world's experts on it. And but you'll see these similar kinds of things that come up in GPU level parallelism. Okay, so now we have a little bit of parallelism. We have to worry about some things if we start doing work in parallel. So we're going to do multiple, say, some operations in parallel inside of one of these registers. We have to worry about data dependencies in the original program. So we wrote a serial program. We expected this statement to execute before this next statement, before the next statement, and so on. And so you need to worry about, or the compiler needs to worry about, when these things can be done in parallel or when they can be reordered. So it's often easier to think about whether they can be reordered, because that will tell you often whether they can be run in parallel. So just to give you some really simple examples of the problems, these are called the various hazards or dependencies that come up in the program. So the first one is a read after write. So I'm reading. I'm first of all writing the variable x, and then I'm reading the variable x in this code. So I wrote the code, it said x equals a, and then it said b equals x. So imagine that I tried to simultaneously do a load of x and a store of x at the same time. I wouldn't necessarily get the right value in the load, right? I might get the value before the write rather than getting the value after the write. Similarly, if I do a write after read, then I might accidentally get the value that happens after the write rather than the value that was supposed to come before the write in the second example, the write after read example. And write after write says if I'm writing both a and b, if I'm writing both a to x and then later b to x, I want to make sure b is the final value that ends up in there and not a. And so these are all places where you've got problems with the dependencies. And the one case that's missing, if you look at all combinations of read and write, is the read-read case, because that one's not a problem because there's no dependencies. You can read them both simultaneously, the same variable, and it doesn't cause any problems. Okay, so this is something the compiler is trying to figure out about your code in order to automatically generate SIMD instructions, and you will need to think about if you're going to probably put in intrinsic operations in the code to try to coax it to use SIMD instructions or other kinds of parallelism. So Now, the last thing, which is not strictly speaking a parallelism thing, is that different arithmetic instructions really don't have the same cost. And one of the operations that's so common in parallel, or combinations of operations that's so common that a lot of processors will optimize it for as a single cycle operation, or one that can be has a bandwidth or a throughput of a single cycle, is a multiply-add combination. So this is used in matrix multiply, and it's called a fused multiply add. It's a particular hardware instruction that says do both a multiply and an add. And so, and here's the formula that it is doing. It's going to take some value c times, say, z, and then add that to y, and then do a floating point rounding calculation after that, and then put the value back into x. And so imagine these are 64-bit values, and the rounding thing is important. And Jim is the expert on this, and we'll talk about it more maybe when he talks about matrix multiply in the parallelism case, but or when we talk about some of the other floating point operations that we do. But it is important that it's only done with a single rounding error, in terms of that intermediate value of the multiplication is stored in a wider value, so that it doesn't round twice. Okay, so what does all of this mean to you? In theory, the compiler understands everything. The compiler just generates the code for you. It will automatically generate fused multiply add instructions, so you don't need to worry about them. And it will automatically understand that you don't have any dependencies, you don't have any of those hazards inside of your code in places where you don't have it, so it can generate SIMD instructions, and it'll do that, so it's preserving the dependencies but generating those codes. In practice, the compilers will need a lot of help. You can try different compiler flags. I think we are standardizing on, you're using GCC, right, in this homework assignment. In the past, we've also let people try different compilers, but that makes it really hard to test out your code and grade it and things like that. So you are going to just use GCC in this class. And you may want to rearrange things in your code to make it kind of more obvious for the compiler that it can do things. And you may want to use special intrinsics, things that are in in GCC in the compiler that you can put into the language that tell it, for example, this is a constant variable and stuff like that, that will make it easier for the compiler to generate optimized code. And you can write, can they write assembly in homework 1, or we say no?
Strongly discourage that.
Strongly discourage.
You get 100% without writing it.
Okay, do not write assembly. It makes the TA's life really miserable when people do stuff like that. So, but in practice, if you're out there optimizing codes, people often do have to write assembly. Okay. Questions about processors, and this is going to be a hands-on experience. This is a graduate course. I have not told you exactly how to do the homework assignment. You're going to get the code, and you're going to try a whole bunch of different things, and some of them will be hopeless failures, and some of them will hopefully work. So, okay. Yes?
Question about concurrency issue, dependency.
Can I throw this to you?
Hello?
Oh, I don't know. Go ahead and give it a try. Oh, I'm getting back. Okay, I'll repeat the question.
The question is, in the case of read after write or write after read, does the compiler just make the instruction to wait until the write finish or something?
Yes, right. So the question is, when you've got one of those hazards in the code, like the write after read or read after write sort of thing, then what will happen is the compiler will just not try to SIMDize that code, or not try to issue those instructions in parallel. And for example, it'll actually issue things that force the memory to go all the way out. You know, the instruction, the data to go all the way out to the slow memory before it issues the next one if it can't be sure.
But there might be a dependency issue with SIMD operations as well, right? So
there might be what? Concurrency issue?
Dependency issue with
yes.
When you use SIMD operations, you use intrinsics, right?
Yeah.
And so there are different latencies and stuff. So if do I have to reorder my code, or I don't know,
So the general question is about SIMD instructions, and the answer is yes, you may have to reorder your code in order to take advantage of the SIMD instructions, and you need to worry if you're going to put intrinsics into the code that say, do this thing in parallel, do this SIMD operation, then it's not up to you, not the compiler, to figure out whether or not there are hazards in that, there are dependencies in it. And so the compiler is going to trust you if you tell it, I promise that these things can be executed in parallel as a single SIMD instruction. It won't check it anymore. Okay. Yes?
It seems the write after write cases is not that dependent, right? I mean, the value of x doesn't have any relation to the value of A, right?
So the question is, does the right after right example seems a little bit silly, because why do you even have the statement x equals A if you're going to immediately say x equals B? And you're right. If they were right next to each other in the code, you could imagine the compiler would be smart enough to say, oh, don't even execute that x equals A statement because there's an x equal B immediately following it. However, this is a really simplified version of the code. Imagine that x is not just a simple variable x, but is an array statement, and maybe it's even got a complicated index expression inside of it, like, or call a function to figure out what I is, and it's really x of I rather than just x, or x of f of I, and then the compiler has no idea whether or not they're going to go to the same location. But yes, it's a very good point that as written there, it's kind of silly to even worry about executing x equals A. Other questions? Okay, yes?
How do I know if I'm actually executing SIMD instructions? So if I reorder my code, how do I know I did something?
Well, you're going to measure it in order to see how well it's performing. But you're going to also be you're putting in intrinsics in order to. Do you want to add something, Alex?
Yeah, for sure. So you can actually pretty easily explore what.
Try this.
Oh.
We'll see if it works.
Do I have to throw it?
No. You just have to. You talk into it.
So you can actually pretty easily explore what assembly code your compiler is generating, given a piece of C code. This is hilarious, isn't it? Given a piece of C code. So there's this great website called gcc.godbolt.org. This is linked in the homework assignment. That shows you basically a color-coded side-by-side view of your C code and the assembly that it generated. And you can see very clearly whether or not SIMD instructions are appearing in there based on the use of YMM, XMM, ZMM registers, because those are what operates in that.
I heard that not only the compiler will reorder your code, but CPU might sometimes rearrange your code at runtime, right?
Yeah. CPUs can rearrange instructions as long as there aren't hazards between them.
How do we know its results?
Can you repeat the question?
Sorry. Yeah, the question was the fact that CPUs can reorder instructions dynamically as they execute code, and your question was, I guess, how to see what that's doing. Yes. I think you might be able to see that with Intel's vTune inspector, maybe, but generally it's unpredictable, and so it's not gonna make or break your assignment. That's the bottom line here.
It's going to depend on whether it goes faster or not.
Yeah.
I think that's the bottom line. Okay, any other questions? Great. I'm glad we're here. You're here to talk about the homework. Okay, all right. Let's see, we did this one already. All right, a little bit on matrix multiply. So we're going to talk a little bit about how to understand the performance of matrix multiply. Why do we use matrix multiply in this class? It's an important kernel that comes up in a lot of linear algebra algorithms and simulations. It's the bottleneck inside of the top 500 list, which you may or may not care about. It's one of the motifs of parallel computing that I talked about, and it's closely related to other algorithms you do on graphs, like transitive closure, the transitive closure algorithm using the Floyd-Warshall algorithm. It also dominates the training time, and I think it even appears in inference in deep learning. So for all those reasons, it's useful to understand how to get matrix multiplier to run fast on the various hardware. Plus, the techniques you're going to use here often come up, and it's one of the best cases for memory hierarchy optimizations in terms of the difference between the best and the worst case. So this is a graph from a former student in this class, David Bindel, who's now a full professor at Cornell University. And so he took the class a while ago, as you can imagine. So DSB is David Bindel's code. That's the blue optimized line up there at the top. The y-axis here is the megaflop rate. And so he's getting about 1.8 gigaflops on this particular, I think this is on his laptop. And the the x-axis is the dimension of the matrix. So he's trying different matrix sizes. So what are you seeing from the naive code? and I'll show you what the naive code looks like a little bit, you're seeing that when the matrix gets to be too big, the performance really crashes, okay? And that's because it's no longer fitting into the memory hierarchy, right? There's a blocked version of the code that's somewhere in between, so that may be more like what your homework will look like inside of here. And by the way, there's vendor optimized code. That's what it looks like relative to David's code, and relative to sort of a blocked code, which might be what your homework assignment looks. So it's fine if you get something close to more like that blocked assignment. I don't even know exactly which processor this one is, but I will say that one of the first times, I think the first time we gave this assignment in this class, some of the students realized that they could outperform the vendor optimized matrix multiply routine. And that was done, by the way, by writing assembly code, so not what you have to do in this class, and also writing what we call a little auto tuner to figure out what was the fastest order of the instructions inside of that inner loop. And so anyway, you can get very ambitious if you want to in homework 1, but make sure you get something that's running first and ready to submit. Okay, so when we're talking about matrices, we need to worry about how they're laid out in memory, because remember I told you about how caches work a little bit, and that you need to worry about the addresses things are at and things, because they might not all fit in the same cache line. If they're all stored at the same offset, say last trailing bits of the address in memory, they may knock each other out of the cache. So a matrix is a 2D array of elements, but the memory is one-dimensional, and so there's two conventions for matrix layout, and there's the Fortran default, that's Jim's preference, which is column major, and there's row major, that's my preference, that is C major, the C default, which is row major. And so you can see what that means is if you've got your same two-dimensional matrix, in the column major layout, the second thing sitting in memory would be the first thing in the second row, whereas in row major layout, the second thing in memory would be the second thing in the first row. Okay, so either one of them is reasonable, but you do need to know, and this is one of the problems you have if you're calling C from Fortran or vice versa, or C++, Fortran from C++, you need to worry about these kind of matrix format issues. And what this means is that now thinking about kind of my cache line behavior, or my cache behavior, all of my indexes that might live at, say, the green row of this matrix on the right-hand side is showing the different cache lines. Sorry, the vertical lines are showing the different cache lines, and that green thing is a row of the matrix. So see what a bad layout that is in memory, in the sense that you've got all these cache lines and it's not aligned or anything, and so that row of the matrix is using all these different cache lines. And what would make it a little bit better is if you happen to have a matrix dimension that was at least a multiple of the number of cache lines, so all of these red things would be lined up. And so that would mean that when you get to the next row, even though it's a column major layout, when you get to the next row, you'd load a whole bunch of these cache lines, but then you get to run a number of rows of the matrix operation before you load any more cache lines. And so anyway, it's just, you have to think a little bit about how these things map in memory. Okay. So we're going to start by using a simple model of memory to optimize. And typically in this course, I think people often do better if they only do look at a single level of optimization, maybe 2 levels, registers and caches, but a lot more than that tends to not work as well. So we're going to have a simple model where all of our data starts in slow memory, and it is going to have the M is going to be, in our model here, is going to be the amount of the number of memory elements, so the number of words that are moved between the slow and the fast memory, either in read operations or in write operations. So that's our measure of bandwidth, the volume that we're going to be measuring. And then we've got the time for each slow memory operation, and we've got the number of arithmetic operations, F, and we've got the time for each arithmetic operation, and so which is much faster than our slow memory operation. So T sub F is much faster than T sub M, or much smaller. And then we've got something called, that we use Q here, which is typically called the computational intensity. And that is the number of floating point operations we're going to do divided by the number of slow memory operations we're going to do. So F over M, and remember going back to some of those graphs I showed from John McAlpin, we really want to be able to have a high amount of computational intensity because some of these processors require that you do hundreds of arithmetic operations for every one of your slow memory operations. So your computational intensity, and a lot of the literature will call this CI for computational intensity. In this class, we've pretty typically used Q, but I wanted you to see both of them. That's the average number of floating point operations per slow memory operation. So the minimum possible time that an algorithm could take, well, it's bounded by a couple of things, but the first one that's most obvious is it's the number of arithmetic operations you have to do. And in this assignment, you're not going to be changing the number of arithmetic operations. You're going to do exactly the same number of multiplies and adds to do the matrix multiply. So that's multiplying f, that number times the speed of those floating point operations. In practice, you have to take into account not just the speed of the arithmetic operations, but also the number of memory operations, slow memory loads and storage you have to do times the rate at which the time it takes to do each one of those slow operations. So I can do a little bit of algebra and rewrite that in terms of Q. And so what you can see when you rewrite that is that a very large Q means that you're going to get closer to that optimal time, f times TF. Right, because this whole term is going to go to 0, and you're going to end up with f times TF. Whereas and so you need Q to at least be greater than the memory time divided by the floating point time in order to get at least half of the peak speed by making these two terms equal. Okay, so that M over TF is often called the machine balance. So that computational intensity is an algorithmic number. It says for my algorithm, or for my kind of execution of this algorithm, how many floating point operations I'm going to do per memory operation. Whereas the other one is really a question of the efficiency of the hardware. What do you require? So we're going to start with a warm-up exercise which is matrix vector multiplication. So here I've got two nested loops, an I loop and a j loop, and we're just multiplying y sub I times aij times x sub j. And so this is kind of what it looks like pictorially, which is I'm going to take a row of A and do this multiply each corresponding row in a dot product. So what does this look like in terms of the computational cost of it? So once again, one of the things I can think about doing is reading. I'm going to assume my vector x is fairly small, and my vector y is fairly small, and they're going to fit in my fast memory. So this is maybe not true for a given architecture and a given matrix size, but let's assume that they fit in my fast memory. So I read them into memory all at once. I can probably read them at bandwidth speeds because I'm reading a big chunk of memory, and then I start my loops and I read a particular row of A, so I assume that A doesn't fit into my fast memory. So I read one row of A into the fast memory, then you do the computation and you write the row of Y back out at the very end. Sorry, when you're done with the iterations, you write Y vector back out. And so what does my computational intensity look like? Well, I'm doing this number of slow memory operations I'm doing is 3n for the different vectors. That's the two loads of the vectors x and y, and the right of the vector y at the end, and then the n squared loads that I have to do of the matrix A. And the number of floating point operations is 2n squared, because that's just you've got one for every matrix element that's in there, or two for every matrix element, a multiply and an add, and then I end up with a computational intensity, which is very low, of 2. And you can tell that this is never going to run at anywhere close to the peak floating point performance of the machine. And that is just true. It's pretty inherent in this problem. There's nothing much you can do about the fact you've got to read the entire matrix A, and you're only going to do two floating point operations in every element. Okay, so that's why we don't give you a homework assignment that says optimize matrix vector multiply, because you wouldn't actually see very much from doing lots and lots of optimization, although there are some things you can do. So let's look at matrix multiply now. So now we've got 3 nested loops, and there's our statement for matrix multiplication. I'm going to update each Cij, but let's do the kind of naive version, which is going to look a lot like matrix vector multiply. So in this version where I'm just running through these different loops and updating each element of Cij, so I've got an element of Cij, and I'm going to do the dot product of this row of A and the column of B in order to update this, because I'm running through J and through K in order to do that. Okay, so what does this computationally intensity look like? So this algorithm has two n-cubed floating point operations, or order n-cubed floating point operation, and it operates on 3n squared, or order n squared memory. So the computational intensity Q potentially could be as large as order n. That is, I'm going to do order n floating point operations, particularly 2n order operations for every single load and store that I do in the memory. Now that's not what's actually going to happen in this naive matrix multiply, but that's my potential is that I could get my computational intensity up to order n. So if I've got a matrix of size 1,000 by 1,000, then I could be up there at the level where we've got a balance, we've got enough arithmetic work to hide all of that memory cost. But what do we do if we kind of look at this code and we annotate it with the memory traffic? So we're going to first read a row of A. We're going to read a column, we're going to read an element of C and read a column of B. And then we're going to do this thing that looks like the matrix vector multiply and then write that element of Cij back to slow memory. And so this naive matrix multiply, and I won't read through every line in here, but you're going to, the amount of memory traffic is going to be order n cubed because you need to read each column of B n times, and then you read each column of A once, and then you need to read and write each column of C. So it turns out then your Q, in this case, your computational intensity is really only still about 2. And that's because it really looks kind of like the original algorithm did. Okay, so what you want to do in homework 1 is to build a tiled matrix multiply. And a tiled matrix multiply will add some more nested loops inside of the outer 3 loops. Okay, so I'm going to do a couple things, and just to make it clear, I'm going to define a block size b, little b, and my block size b is going to be defined as my original matrix dimension n divided by some capital N. So think of capital N as some tuning parameter that you're going to play with and try to figure out what capital N should be. And so my outermost loops are going through the blocks, and my innermost loops, which are not really written out here, so this matrix multiply in the bottom here is saying C sub ij, etc., is do a matrix multiply on a block. So what does that mean? That's really 3 more nested loops inside of there. You may find that you want 5 rather than 6 total nested loops, but you've got 3 more nested loops doing the matrix multiply on the little block of C to compute a little block of C based on a little block of A and a little block of B. So you multiply those 2 little blocks together, add them to C, that block of C, and then write that block out. And so this is now how think about this. You want to read this block of C into fast memory and so on. And question?
So any insight on how to determine block size?
So the question is, how do you determine the block size? So that is going to be a great question for you to think about in the homework assignment. You do want to think about whether you're tiling in order to what is your fast memory that you're looking for. And so one hint would be figure out what the cache size is on the Haswell processor. If you're going to optimize for, say, the level 1 cache, and you know you got to fit 3 blocks inside of it. You got to fit A, B, and C. So you might kind of think about what that block size should be so that they fit inside the cache. And there's a whole bunch of papers on tile size selection that say, and then you divide by 2 or something like that. So there's a bunch of experimentation in here in addition to lots of performance models you can do, but that is something you'll be exploring. Okay. Okay, so that's the block size there is the loop bounds on those innermost loops. So I didn't write out the code with the 6 nested loops, but hopefully that's clear that that's what you're actually doing is writing this that now has more nested loops, and the outer ones are just jumping through different blocks, and the inner ones are doing the actual matrix multiplies on blocks. Okay, and let's see. Okay, the cache. Remember, if you're tiling for cache, oh, by the way, you can also tile for registers. So that innermost loop, those 3 innermost loops could be really tiny loops that go from 1 to 4 or something like that, and you might be able to unroll those and turn them into code that is just sort of doing a set of instructions that does a little tiny 2 by 2 matrix multiply, so from 0 to 2 or something like that, or 1 to 2, But now if you're tiling for cache, you're going to hope that the cache automatically does this for you. That is, reads a block of CIJ into fast memory and reads these other blocks for you. You don't write code that says read this stuff into the cache because you don't control the caches. Remember, the caches are automatically looking at the addresses, figuring out what things fit in cache, putting them in there, and knocking out things that no longer fit in cache. So this is where why it becomes there's a lot of experimentation involved in this, and it is also why you may want to do some other optimizations to get your code, your matrices. Remember that one I showed you where the columns were all kind of off by a little bit as you went across the rows. So you may want to lay things out in such a way that you've got a nice contiguous chunk of memory that's maximally using your cache. So you might want to pad your matrices so they're a multiple of the cache line size. Okay, so just to give you some idea, some other performance numbers. So this is looking at the performance of matrix multiply versus the matrix vector multiply. We will call these, and I'm running a little short on time, so the DGEM-B, the vector matrix multiply, is called a BLAS2 routine. Those are vector operations, and the vector matrix operations, and then the DGEM-M, so the matrix multiply, is matrix operations. Okay, so if we do the analysis on this, what is the amount of time that it takes? How much memory traffic do we have to do for tiled matrix multiply? So let's just try to look at the red statements in here. So we're going to read each block of B capital N cubed times. So remember, capital N is the number of blocks in each dimension of the matrix. It's not the total matrix dimension, which is little n. So we're going to read that n cubed times, and similarly, we're going to read a block of A n cubed times, and n cubed times the block size. So how much data do I have to read? It's really that n cubed times the size of each of those blocks, which is little b squared, and that's equal to this formula. So we get capital N times little n squared. And similarly for the A matrix. And then for the C matrix, we read and write it once, and in that case we can look at the details of the arithmetic, and you get 2 little n squared. So we still have to read and write every element of the C matrix exactly once. But this is really where you're getting your performance savings, and your memory savings is on the way you're walking through the A and the B matrix. So the computational intensity here, Q, is, remember, the floating point operations is divided by the memory traffic, which is just taking these formulas, dividing it by the 2n cubed flops that I have to do for matrix multiply, and dividing it by the memory traffic. And so that's going to turn into roughly B for a large value of for a large matrix size. And so we're going to get much better computational intensity and much better performance than for the matrix vector case or for the naive case, which was only Q is equal to 2. Now, it turns out there's a theory that says how much data do you have to move from slow memory to fast memory in order to perform a matrix multiply operation. And actually in the paper by Hung and Kung, which is a classic one, it also talks about some other algorithms like fast Fourier transforms that you may hear about later, you will hear about FFTs later in the semester. But this says that, this theorem says that the amount of the computational intensity, that matrix multiply fundamentally has a computational intensity of order M, capital M now, sub fast. So that's my size of my total cache size, the square root of that. Okay, so a little intuition here is think of my cache as holding some little B by B matrices, and so that tells you something about that's why I kind of think of that cache as the square root of that is going to give you my computational intensity, because that's how much intensity I have, right? In matrix multiply, it's order n, where n is one of the dimensions of the matrix. And so this result in the paper says that if the amount of useful work that you can do in matrix multiply is bounded by, if you've got exactly whatever data you want into your fast memory, the amount of work that you can do is this square root of capital M. Okay, so that gives you some lower bound results. Let me give you a little bit of practical stuff. Somebody asked about tile size. How do you select the tile sizes? These are some experimental results looking at a whole bunch of different tile sizes along the x-axis. And just the point of this, without reading through the specific details of what's on this graph, is it can be highly unstable, right? You can get performance that really depends a lot on exactly what your cache looks like and what your tile sizes look like. Tuning code can be pretty tedious, and so you can try to build a model, an analytical model that says my cache is this big, it has, four-way associativity, it can hold, each cache line is this big, and you can try to multiply this out, but it's really hard to come up with a model that's simple and accurate. For some of these, there was somebody that did a very detailed performance model of one of the processors about 10 years ago, and it was many pages of formulas in order to get an accurate model of what was giving you an accurate model of what the performance was going to look like. The second thing you can do, which I mentioned earlier, is auto-tuning. That is to say, I'm going to just try a whole bunch of things, and you might write a little piece of code that tries a bunch of different tile sizes. You might do that manually, but you also might try to do it automatically, and we call that auto-tuning. And that was also a result that came out of this class, was somebody who wrote an auto-tuner that was doing this kind of search through the different tile sizes. So this is a heat density heat plot that's looking at the two different dimensions for register block sizes. So this is looking for the little tiny blocks that fit in registers, and red is the higher performance. And so you can see right here that there's this one data point. We call this looking for the needle in the haystack because it's pretty hard to just guess that that would necessarily be the right size. So let's see. You're going to want to minimize communication between all different levels of the memory hierarchy, but you'll have to figure out which ones you want to explicitly try to optimize for. And just pointing out once again that each one of those levels, if you're tiling for that level, you're going to turn that into more nested loops of code for matrix multiply. There is a technique called cache-oblivious algorithms, which is more of a recursive approach to this problem, and some people have tried that in the class as well. So what does that basically look like? At a high level, I take my matrices. I'm going to just think about this, the first level of recursion. Think of my matrices divided into 4 blocks, and now I can write the matrix multiply this way in terms of the blocks. So I'm going to just multiply these corresponding big blocks, and then we're going to end up with, doing the computation that way. If I do it recursively, in theory, what happens is I eventually get to a small enough block size, because the way I'm going to do these little blocks, the A11, is by dividing it into even smaller blocks and so on. I'll eventually get to blocks that actually fit in the cache. And so there's papers that show that these are optimal. There is a little bit of a trick in terms of the cost of the recursion, because that involves a function call can be fairly high, and so you have to be careful that you don't go sort of too far down the recursion. And so this is what the code looks like for the recursive matrix multiplication. And I don't have time to do the analysis, but it is in the slides if you want to go back and look at the analysis. And I think that the last thing I'll say is that people often use recursive data layouts as well. So that means the first thing you might do is a copy optimization, and that would be changing your data structure to live in a different format in memory. So for example, that first little purple block is all next to each other, and that way when you're doing the blocked matrix multiply, all the things are contiguous in memory and will end up nicely lined up in your cache. Did you want to say something?
Yeah, I did.
Okay. All right.
I just also wanted to mention that I'm going to be holding the class's first office hours tomorrow from 4 to 5. So if you want to come in and talk about any of performance optimization kind of stuff, definitely drop by. All the details are on the course website.
Great. All right. Thanks very much.